Hello and welcome. My name is Dr. Mark Taylor, and this is the first of a series of videos reviewing the Deltec Physics 111 Exam 2 Preparation and Practice Exam covering forces and energy. At this point, I'm going to pause the video and we'll switch over to the practice exam itself. Okay, so here's the cover page of the practice exam, and sliding to the next page, you'll see it's a list of the forces that you need to know for this course. Applied force, gravitational and weight forces, normal force, friction, tension, and net force, also known as sum of forces. And the headings are the force name, the abbreviation, definition, formula if you are required to know it, and the direction of that force. So let's start with the abbreviations for each of these forces, and it's always the same format. The forces are going to be abbreviated with a capital F and some subscript telling you what kind of force it is. So applied force is F sub APP. Gravitational force is F sub lowercase g. And so is the weight force, because the weight force is just a special type of gravitational force, and we'll explain that in a second. The normal force is with an uppercase N as the subscript. The friction force is a lowercase f. The tension force is with a uppercase T, and some people will actually just abbreviate tension force with a capital T by itself and the normal force with a capital N by itself. But we're going to label everything with a capital F just to keep it simple. And then the net force is force sub net, but you could also write this as the sum of forces because that's what it is. All right, so let's go through each of these forces one at a time, and we'll do the definition, the formula, and the direction for each of these. So the definition of an applied force is really just a push or a pull that's applied to whatever object we're interested in. And the formula is going to vary, so we're not going to go over that, and typically will give you the value of the applied force, but not necessarily. And it's always going to be in the direction of the push or pull. And I recommend that when you are told of an applied force on an object, draw it as if it was a pull. So if it's a push in one direction, pull it in the same direction using arrows away from that object. It'll just keep your drawing simpler. Gravitational force and weight force are highly related. The weight force is just a special case of gravitation, as I mentioned before. So the gravitational force is the attraction between any masses, okay? And it doesn't matter how big or small those masses are, but when the mass is between an object and the Earth, we call that force, that specific gravitational force, we call that the weight. So it's the force between an object, and an object in this case can mean a person or an animal or any object, and the Earth. Okay. And we have a formula for gravitational force. We've done it in class, but you're not responsible for it. So I'm just going to leave it out here for the meantime. You can write it in if you want. But for the weight force, it's a very simple formula. The weight force is just equal to the mass times the acceleration due to gravity. This is typically minus 9.8 meters per second squared. Sometimes we might use 10 meters per second squared. And depending on the context, we'll keep the negative sign or leave it as a positive sign. And gravitational force between any two masses, that force is pointing to both masses. But when we're talking about weight, since it's the force of attraction between the object and the Earth, specifically it's the force of the Earth on the object. So I'm gonna change this. It's the attraction by the Earth on an object. But either definition is fine. And in this case, that force is going to point straight down specifically to the center of the earth. And you could write this any way you want. Now, a normal force is a force that's provided by a surface that's supporting some object. And we refer to the normal force as a support force. So to have a normal force, you have to have something supporting the weight of something else. That could be the ground, that could be a table, that could be the floor in your home, etc. So this is a force that's perpendicular up from the surface. So if you tilt the surface, the force is still coming up from the surface perpendicular to it. And it's important to understand that it's always perpendicular. And this force supports any object on the surface, and it prevents it from penetrating the surface. In other words, falling through the ground or falling through the floor or through that surface. Okay. And we don't have any specific formula for normal force, but if, and I'm going to put this in parentheses, if normal and weight are the only vertical forces, then normal will equal the opposite of it'll be the same size, but in the opposite direction of the weight. So the normal force is always going to be perpendicular up from surface, the supporting surface, I should say. Supporting surface. All right. Now, friction surface, this is a force, the friction force, this is a force caused by rubbing of one surface on another. So a force caused by rubbing between surfaces, and it tends to slow down or even stop motion by one of the surfaces, by one object on the surface. And as a result, the direction of the force is always in the opposite direction of possible movement. I say possible movement because the friction might be high enough to prevent movement. And we have a formula for this. And the formula for calculating friction force, we calculate it from the normal force. I'll make that a little bit bigger. You can see it. That should actually be force of friction. Make that lowercase f. It's a little hard to see there. So it's equal to a constant. The letter mu is what we use to represent that constant. That constant is called the coefficient of friction. I'm sorry, we don't multiply it by the friction. We multiply it by the normal force. So if you know the normal force, you can calculate the friction force, but you also need to know the coefficient of friction. So typically what will happen is you'll figure out what the weight is. You'll be given a mass. You'll calculate the weight, m times g. The weight will frequently give you information about how big the normal force is, and the normal force can then be used to calculate the friction force. So frequently you'll be doing them in that order. Calculate the weight, calculate the normal, calculate the friction. The tension force is a force along the length of a taut, and it has to be taut, stretched out, taut rope or cord or a wire, etc. And as a result, the force itself is always along the length of the taut cord, etc., in both directions at the same time. And we don't have a direct formula for that, so it's going to vary depending on the situation. Now, the net force is literally just the sum of all forces, and it might be the sum of all forces in the x direction, or the sum of all forces in the y direction, and when you add those together, it's the sum of all forces total. And it could be in any direction, depending on what forces you're adding together. So it could be in any direction, or it could be net force of 0, in which case there is no direction to speak of because there is no force. And we don't have a specific formula for that, but you basically add up the individual forces, and those could be, like I said, in the x direction first and then the y direction, or if you know how to use trigonometry, which we don't cover in this course, you could add them all together and get one net force right away. So those are the forces. Now let's switch over to the energies. So in this table, we have the names of the energies, and we have a variety of energies: work, kinetic energy, potential, gravitational potential, elastic potential, mechanical energy, non-mechanical, heat, and total energy. And then you're asked to fill in abbreviations, definitions, just like before, formula if known, just like before. And then this last column, it says dependent on, so you're asked to say what property each type of energy is dependent on. What are the most important properties that change the amount of energy in that category? All right, so the first one is work, and we'll just do the abbreviations first. Work is W, that's pretty straightforward. In fact, all of the abbreviations are pretty straightforward. Kinetic energy is KE, potential energy, PE, not surprisingly. We have two types of potential energy that we're interested in this course, the gravitational potential energy and the elastic potential energy. When you add kinetic energy and all types of potential, you get mechanical, and we'll talk about that in a minute. And then the remaining type of energy is the non-mechanical energy. Heat is one of the several types of non-mechanical energies. We abbreviate it, with a Q. Sometimes you'll see it abbreviated with a lowercase q. It's one of the few things in physics where the uppercase or lowercase are used. And then total energy is TE. And let's look at some of the definitions here. So none of these are really things you measure on their own. You can calculate them, and you typically measure them as the energy is being transferred to some other object and frequently transformed from one form of energy to another. So work is a transfer of energy when a force is used to move an object by a specific displacement or distance. You can think of it as distance in this case. Now, you'll notice the answers I'm typing in might be slightly different from the answer key. That's fine. They're just different ways of wording these things. And work, we have a very specific formula. Work is equal to the force times the distance. And there normally is another third term in this formula, the cosine of the angle between the force and the line where the distance is going from one place to another. But we're only going to do examples where the force is always pointing in the same direction as the distance or displacement where the object is being moved. So we're not going to worry about that other thing. But you should know that with vertical work, the formula becomes work equals its force, but now the force is specifically the weight force, and it's times height. as opposed to horizontal, where you need to know what the applied force is for that work. And work is going to be, because the formula really includes force and displacement. I'm sorry. What is it dependent on? Well, it's dependent on how much force and how much displacement. If there's no force, there's no work. If there's no displacement, you could put all you want. If the object doesn't go anywhere, there's no work there either. Now, kinetic energy is the energy due to motion. You have to have movement of the object. And the formula for that is 1/2 times mass times the speed. It doesn't have to be a velocity here. Speed is good enough because the energy doesn't care whether what direction the object is moving. If the object's moving in any direction, that's going to impart kinetic energy on the object. So mass is important, but you can see that the speed is squared in the formula, so speed is the most important, but also mass. Now, potential energy comes in lots of forms, but the general rule is it's energy due to some special position of an object or orientation or configuration. You can use whatever word you want, and that could be different things for different types of potential energy. So potential energy is going to be the sum of all the individual potential energies. And it's going to depend on various things, but special positions or orientations, or like I said, you can use a variety of words for that. So the two types of potential that we're interested in this course are gravitational potential energy and elastic potential energy. And gravitational potential energy is energy, specifically, we'll say potential energy, due to an object being above the ground. You could word this more technically, above the surface of the earth, but it's essentially the potential to fall down and start going faster and faster and turn into kinetic energy over time. So if you held an object up a certain height, that object would have a certain amount of gravitational potential energy, and we would calculate that by calculating the force of that object times the height of that object, which you'll notice is the same formula as the formula for vertical work. Because if I add another term in there, force of gravity is m times g, and then height is h, so vertical work is mgh. Well, so is gravitational potential energy, and that is because you have to do a certain amount of work to lift the object up. Okay, that's the weight force, mg, times its distance, which is the height, h. Well, once it's up that high, the object now has that energy, and we call that gravitational potential energy. It's basically the potential to drop down and speed up as it does that, and we calculate that the same way, mgh. And as a result, height is something that's very important for changing the gravitational potential energy of an object, but mass is too. Mass is also important. But typically you're talking about a specific mass. We're not changing the mass, but you can easily change its height. You can just move it up higher and it has more gravitational potential energy. Move it down lower, it has less. Now, elastic potential energy is a potential energy due to what we'll call a restorable object, but I'm just going to say a stretchy object. and that can be a lot of different things. Stretchy object being either stretched or compressed. Doesn't matter as long as that object can stretch back to its original position. In other words, it's restorable. And you'll see slightly different wording in the answer key. I'm giving you a couple different ways to think about things. And we have a formula for this, but you're not responsible for the formula, so I'm not going to write it down in that box. But the most important thing for determining how much elastic potential energy an object has is how much it's been stretched or compressed. Now, mechanical energy is just the sum. It's just the sum of the kinetic energy and all the potential energies. And if you want a definition, it's supposedly energy that can easily be converted to work energy, right? But the better way to think about it for your purposes is it's the sum of kinetic energy and potential energy. And not surprisingly, the formula for that is kinetic energy plus potential energy. If you're looking at an object falling, so let me put that here, for a falling object, ME equals KE plus the gravitational potential energy. We're not going to worry about the other kinds of potential energy. It's just the sum of those two. So obviously mechanical energy is dependent on how much kinetic energy and how much potential energy you have in a system. Non-mechanical energy is any remaining energy that's not mechanical energy. So the non-mechanical energy will include a variety of different energies. I could give you a definition here, which would be that it's energy that's not easily converted to work energy, but I'm just going to list the types of energy for your purposes that you really need to know about. So it's a mix of energies that are not easy to turn into work, like heat and sound energy and deformation energy. Deformation energy is the energy of breaking or bending something that's not going to stretch back to its original configuration, right? And how do you calculate it? Well, the non-mechanical energy is just the total energy minus the mechanical energy. And that is because of a simpler formula, a simpler version of that formula, which basically says that total energy equals mechanical plus non-mechanical energy. So they're the two versions of the same formula. And the non-mechanical just depends on how much energy is turned into heat, sound, and deformation. How much you have. Now, heat is one of these non-mechanical energies. It's also referred to as thermal energy. Thermal means heat. And it's really due to the internal movement of molecules and atoms or whatever particles you're talking about in a substance. And we don't typically measure the heat within something. We measure heat as it's being transferred from one thing to another. And there are many formulas for this, and you're not responsible for any of them in this course. If you were taking a chemistry course, you might learn about 2 or 3 of them. So there are lots of these. All right, so heat depends on the speed of the moving molecules or atoms in the substance. And then total energy, not surprisingly, is the total of all the energies. So total energy is the sum of all energies. And since energy is conserved, total energy in a system, as long as the system doesn't allow energy to escape, usually the total energy, and I should say usually, as long as you're not adding energy to the system or letting energy escape, the total energy is going to be constant. Whatever you started with will be what you end up with. And as I mentioned before, the total energy is just the sum of the mechanical and the non-mechanical energy. So what's it dependent on? It's dependent on how much of each individual energy you have. Simple as that. So that's the energy table. And then the last of these property tables is just properties that don't fit as either forces or energy. So they include things like mass, acceleration, ideal mechanical advantage, power, and percent efficiency. And we've already dealt a little bit with mass, but you use mass quite a bit in the free body diagram. So let's talk about that. Mass has an abbreviation of lowercase m. Make sure it's lowercase. And it's really just the amount of matter in an object, okay? And that could be any kind of object, amount of matter, or you can think of it as the amount of inertia in any object. And objects could be solid, liquid, even gas, even plasma, which is a fourth state of matter, and we actually have many states of matter that you would only learn about in a really specialized course. We don't generally calculate mass, but it is good to know that if you have a weight force, for instance, that you can calculate mass from the weight of an object. If somebody gives you the weight, the first thing you should do, I highly recommend, is figure out, and this is supposed to be divided by, it would just be gravity here. Oops, I'm sorry, that's divided by gravity. So, and that's because the weight force is simply m times g. So if you just rearrange it, m is the weight divided by g, 9.8 or 10 meters per second squared, depending on the problem. So weight is dependent on inertia. You might think I would say mass is dependent on inertia. You might think, oh, mass is also dependent on weight. Well, it is if you have gravity. If you don't have gravity, they're not dependent, because if you have no gravity, you have no weight, but you still have mass. So it's important to understand that. All right, acceleration comes in a couple versions. There's just general acceleration. When the acceleration is the acceleration due to gravity of Earth, we call that g, lowercase g. And it's, as always, it's the change in velocity over a period of time. Right? And we already have a formula. So acceleration, you can write acceleration as the change in velocity over the change in time. But since we're talking about forces now, what you really want to know is how it relates to forces. And the way it relates to forces is you have to know the net force on an object, or the sum of forces. Remember, those are the same thing. And then you merely divide it by the mass to get the acceleration of that object. And I have this formula, written in a slightly prettier way in the answer key, but it's a little hard to type quickly. So what is acceleration dependent on? It's dependent on the net force, and it's dependent on the mass. The higher the net force, the higher the acceleration. But the higher the mass, the lower the acceleration, and that's because mass is in the denominator. All right. And you'll probably be asked to calculate acceleration at some point in one or more problems on the actual exam. So always keep in mind that you have to first know the mass of the object, and secondly, you have to know the net force on the object, and then you divide the net force by the mass, and you get the acceleration. So there are a number of things you have to do first to get that net force. And if you're given a weight, you have to figure out what the mass is from the weight, or we might just give you the mass. So you have to be aware of what we're giving you in order to determine. The ideal mechanical advantage is not surprisingly abbreviated IMA, all caps. And what is this? Well, the IMA is a factor that tells you how much help a machine gives you. Now, a machine will never lower the amount of work energy you have to do. It won't. You can't get energy for free, ever. But what it can do is lower the amount of force you have to use when you're using that machine. So you might have a job where you have to lift something up, and the force you have to use is the weight of the object. You have to apply the same force as the weight to lift an object up. But what if you can't lift it? Well, you use a machine that lowers the amount of force you have to use, but you never get anything for free. And because work is force times distance, if you lower the force, you have to pay for it by increasing the distance. And the machine will have an IMA, an ideal mechanical advantage, and this is a factor that that tells you how much lower a force you can use. It is also a factor for how much more distance you have to use as well. So you always have to pay for that lower force with more distance. And what does that mean? Well, if you're using a ramp, you can use less force to push a heavy object up the ramp, but you have to push it a longer distance. In other words, you have to push it along the long ramp instead of just lifting it up directly. If it was a pulley, you would have to pull a lot more rope than the actual movement of the object that you're lifting up. If you wanted to lift an object 1 meter, you might have to pull the pulley's rope 4 meters to get the object to lift up only 1 meter. Well, the factor is basically the division of whatever's bigger divided by whatever's smaller. So what do I mean by that? Well, what I mean is, and I'm going to see if I can copy this directly here. I don't know if this will work. Nope, it's not working. But the IMA is either the force that you get out divided by the force you have to put in, or the IMA is equal to the distance you have to put in divided by the distance you get out. All right, so what does that even mean? Let me get the subscripts right here so this will look better. It means that the ratio of the force that you're lifting to the force you actually have to put in on your own is going to be some number bigger than 1, and that factor tells you how much less force you can use to get away with doing your job. The machine helps you lower your force, but the problem with that is you don't get anything for free, so you have to put a greater distance in. So if you look at these two formulas, it's basically saying the force out is going to be significantly bigger than the force you have to put in, and that ratio is the IMA. That same ratio is also the ratio how much further you have to pull the rope or push up a ramp divided by how high the object actually goes. That's the distance output. So you want to lift something up, that height that you're lifting it is the output distance. And these ratios are the same, and if you find that you have a ramp and the ramp is 10 times longer on the ramp than it is high, well, that means you can use, you have to push it 10 times further along the ramp, but the benefit is you get to use 1/10 of the force that you would normally have to use, and that 10th of the force is 1/10 of the weight of the object. So it pays for itself in terms of making it easier for you, but you have to do more distance in order to get the two work energies to be the same. The output work, which you're not doing, the machine's helping you do, and the input work of what you're actually putting in to using the machine. So the IMA, which has no units, by the way, because it's always a ratio of force to force or distance to distance, basically tells you how useful a machine is in lowering how much force you use. Now, power, abbreviated with a capital P, power is not energy directly, it is work energy per time. And in other contexts, it's energy per time of any kind. But for this unit, we'll only talk about the work energy per time. So how do you get power? Well, it's very simple. You have to figure out how much work is done, and it depends on which formula you use. But power is just work divided by time. So it's the number of joules of power, number of joules of work divided by seconds of time. So what that means is power is dependent not only on the work energy that you put into doing a job, but also how long that job took. In other words, the time. Now, percent efficiency, there's no real official abbreviation. We'll just use percent EFF if you want to write it with less letters. And this is the percent of your effort that actually results in work energy. All right. So what does that mean? And that's usually by a machine. Well, machines in rare cases are 100% efficient, but frequently there might be friction in the machine, so some of the energy you put into using the machine is lost. The friction turns it into heat, and that energy is gone. You don't get to use it to do work. So the percent efficiency tells you what percentage of the work you put in equals the work you put out. If in a machine that is 100% efficient, the work you put in is exactly equal to the work you put out, but machines aren't always 100%. So you have to basically consider the fact that machines are not perfect. So how do you use this in a formula? Well, the percent efficiency times the work that you put in subscript here is going to be equal to 100% of all the work that comes out. So in practice, what this means is when you look at a formula that has multiplication in it, you can frequently replace the word times, meaning multiply, with the word of. So I'll just read it with the word of, and I'll replace the word, the equal sign with the word is. So if I read this formula, it's a certain percentage of the work I put in is 100% of the work I get out. So if you know how much work you need to put out and you know how efficient the machine is, you can easily calculate the work you put in, the work input. In other words, maybe you need to produce 2,000 joules of work energy, but your machine is only 67% efficient, in other words, 2/3, it means you have to put in 3,000 joules of work on your own to get 2,000 joules of work output. If this was 50% efficient, you would have to put in twice as much work as you actually get out. So percent efficiency depends on the input and the output energy. It's that ratio of the two turned into a percentage. In practice, what it really means is how efficient the machine is. But that doesn't really give you any new information because that's kind of what the definition of percent efficiency is. All right. And the last table I want to cover is a very different table. We're not actually defining anything. All we're doing is looking at all these different properties, and I put them in no particular order so that you have practice working on them. But you're supposed to write down what the unit of measure we use to measure these. This is the Standard International Unit, or the International Standard Unit, which is sort of like the metric unit. And I have a number of different properties here: mass, work, weight, friction, kinetic energy, etc., filling the page. And you're asked to both spell out the unit and to give the abbreviation of the unit. Well, let's do them in groups here. We first learned about forces, and we know that forces always have the same unit. The force of anything is in newtons. And the abbreviation for Newton is a capital N. So anytime we see a force, that's going to be a Newton. Well, weight is a force. Friction is a force. Tension is a force. Applied force is obviously a force. Scroll down, gravitational force, it tells you it's a force. Normal is the normal force, and net force is obviously the sum of forces. So that fills in a number of them. Let's make sure I didn't miss any of the forces. Looks like I got all, looks like I got all of them. Tension force as well. Okay, and the next group of properties we looked at were all the different energies. Well, energies include things like work and kinetic energy and all the things that end with the word energy. And those are always measured in joules. And we use a capital J to represent joules. So let's just look for all the energy terms. There's kinetic energy. I've already done work energy. Next one's gravitational potential energy, or any type of potential energy. Heat is a non-mechanical form of energy, also in joules. And it looks like those are all the energy terms. So we've already filled in a good chunk of the table. Mass, as you know, is a kilogram, and the unit is kg. Abbreviation is kg, both lowercase, as opposed to joules and Newton, which are uppercase. Acceleration is meters per second squared, and you can write it the way you want here. There is no real abbreviation aside from the actual units. If you want me to spell it out, I'll spell it out. It's meter per second squared. There we go. Power is not energy, it's energy per time, specifically in this case, work per time. So it's not joules, it's joules per second, and we call that unit a watt, and we abbreviate it with a capital W. Both joules and watts were actually named for people whose first name was James. It was James Joule and James Watt. Newton obviously was Sir Isaac Newton. Now we also have the acceleration due to gravity. Well, it's an acceleration, so it still has acceleration units. And so I'll just fill those in. And that leaves just two items in here: the ideal mechanical advantage and the coefficient of friction. Well, the ideal mechanical advantage is the ratio of the force you get out, which is a bigger number, divided by the force you have to put in, a smaller number. So you're dividing force by force, so there is no unit. It's a unitless number. And coefficient of friction is the ratio of the force of friction to the normal force. So it's another ratio of two similar things, and therefore newtons divided by newtons will cancel, and it's also a unitless property. And that completes the first few tables, and we'll start with the next video on Newton's 3 laws of motion.